Hi everybody, this video is going to be about finding the domain and range of continuous functions. So in the previous video we talked about domain and range, but it was for functions and relations that had a more restricted domain. Here we're going to get into the situation where we have so many points in the domain and in the range of the function that we can't actually write them all out, okay? Because there's an infinite number of points, and we would literally spend the rest of our lives trying to write them all out if we wanted to, and then not even get done. So we need a better way to do it, okay? And we're going to use inequalities today to help represent the domain and range of these functions or these relations. So for the domain, remember, we're talking x values. And if we're talking x values, that means we really want to be looking to see what x values we have for the graph as we move from left to right along the x-axis. We want to see, are there any x values missing? Is there anywhere where we don't have a graph for those particular x values? For range, we said range was the y values in a relation, so instead of left to right, we want to be looking from the bottom to the top of the graph along the y-axis this time. So here's what that looks like. For number one, okay, remember these arrows mean that this graph is going forever in that direction. So on the left side, our arrow is going left and up forever. Okay, if it's going left forever, that means that it's really extending into negative infinity territory as it moves to the left. And as it goes up and to the right, it's approaching positive infinity. So our x values span all the way from negative to positive infinity, giving us a domain of all real numbers. Okay, now instead of writing all real numbers out, we're going to use this symbol to represent the set of all real numbers. What that means is for any x value that you can think of, okay, as long as it's a real number, you can find a point on this graph that has that as its x value. For the range, we're looking from the bottom to the top. Now, these arrows are pointing up forever, so my y values are going up to positive infinity, but they don't go all the way down to negative infinity. The lowest y value is down here, okay? We don't have any graph that's lower than this line I drew in here. And the lowest y value we have is a y value of -2. So if our lowest y value is -2, and then all of our y values are bigger than that, then we can say the range is all of the y values greater than or equal to -2, because that was the lowest, everything else is bigger. For number 2, if we don't have any arrows, this is a circle. This isn't even a function because it would fail the vertical line test. But it's a relation, and we could still find the domain and range. So this one, since there's no arrows, it actually has a leftmost and a rightmost value. So here's the left boundary, here's the right boundary. And on the left side, okay, that's an x value of -3. On the right side, it's an x value of +3. So we're saying all of the x values on this circle are between -3 and +3, and we could write that as an inequality like this. We're saying x is greater than or equal to -3 and less than or equal to +3. For the range, we have a lowest and a highest y value. The lowest y value is -3. The highest is +3. So very similarly, we can write the ranges, all of the y values between -3 and +3 inclusive, meaning it's allowed to equal those as well. So these can be really tricky. Okay, we're using those inequalities. Make sure you're picking the right symbol. All right, number 3, we have a nice line here. So if you look, each side has an arrow. The left side is going left and up forever. The right side is going right and down forever. So that means our x values are going all the way from -infinity to +infinity. giving us a domain of all real numbers. Now, similarly, the y values are going down forever and up forever, making the range all real numbers as well. Okay, but for number 4, even though the domain is all real numbers, because it's going to from negative to positive infinity for the x values, our range isn't all real numbers because we have a highest y value. The highest y value is found up here, okay, at positive 1, 2, 3, 4. And all of the other y values are lower than that because the arrows are going down to negative infinity. So as an inequality, we would write this as y is less than or equal to positive 4. For number 9 here, so we're skipping on your paper. For number 9, this is a vertical line. So I want you to think about it like this. The x value at this point is 2. The x value at this point is also 2. At this point, it's 2. At every single point on this graph, the x value is 2. So the domain for this function, well, it's not even a function because it fails the vertical line test. The domain of this relation is 2. Every single point on this vertical line has the same x value of 2. Now the range, since it's going from negative to positive infinity straight up and down, the range is all real numbers. For a horizontal line, we're going to have the opposite. Okay, because it's stretching from negative to positive infinity in the x direction, so the domain is all real numbers. But this time, every single point on the line has the same y value, making the range just negative 4. So that's it for this video. It was a quick video over domain and range of continuous functions and things where we can't physically list all the x values in the domain, all of the y values in the range. So we get into these negative, positive, infinity situations where we have a domain of all real numbers, or maybe a range of all real numbers, or maybe we have to use an inequality to represent all of the values in the domain and range. So again, rewatch, pause, and ask questions. Have a great day.